Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to today's lecture on recycle systems with reactions. In the previous lecture we had discussed recycle systems without reactions, and today we will talk about a reactor which, in addition to the fresh feed, will also have a recycle feed. Why do we have to do this? This would increase the conversion in a reactor. The unused reactants which get recycled will have a chance to go through the reactor one more time, which would mean more of the products would be formed, and hence the conversion would increase for the overall process. We need to know how the terminologies are defined for such recycle systems with reactions so that we can apply them. The principle for material balances itself would be similar to what we have done for recycle without reactions. However, when we talk about recycle with reactions, there are certain terminologies which we should be familiar with. Overall fraction conversion is the ratio of the amount of reactant consumed by the overall process, which would be the fresh feed to the output, to the amount of reactant in the fresh feed. So here you are considering the overall process as a single system and calculating the conversion. You can also be given something called a single pass or a once through conversion. So this would be the ratio of the amount of reactant consumed by a single pass through the reactor to the amount of reactant entering the reactor. So here you are taking the reactor as the system and you are not considering the other components in the system. Let me explain this with simple flow sheets which would help you understand the process better. For any system with a recycle, this would be a simplest system. So here what you have is a fresh feed which gets mixed with the recycle feed to enter as the gross feed, and you have the gross product out of which some aspects are taken out as the recycle feed and the rest is sent out as the final product. So what you have here is the fresh feed, and this would be the gross feed, and again this would be the gross product, and this is the final product, and this stream is the recycle. So this is a standard flow sheet for any process with recycle. So in this case we are assuming a reaction to happen, which means this would be a reactor. So when we were talking about the overall fraction conversion, we would assume the entire process as one single system. So this is the overall system. For the overall system, what we have is fresh feed which contains reactants entering, and you have the final product which is leaving. So all the reactants which are consumed within this process is taken in the numerator, and the reactants which is fed through the fresh feed is taken in the denominator to calculate the overall fraction conversion. So this would be total reactants consumed in the overall process divided by reactant fed through fresh feed. So this is the overall fraction conversion. The other conversion which we looked at was single pass or once through conversion. Let us again draw the similar process where you have a reactor and a fresh feed and a recycle feed mixing to form the gross feed. For the single pass or once through conversion, we are accounting for reactants which are passing through the reactor only once, which means the system chosen for studying would be the reactor alone. So here what you have is the reactants entering through the gross feed pass through the reactor only once and leave as the gross product. So, the reactants which are entering into the reactor get converted or consumed to form the products. So, here your single pass conversion then becomes reactant consumed in the reactor for a single pass divided by reactant entering in the gross feed. So, now what you have here is the single pass conversion. So, you can clearly see that the reactant which is entering this reactor, which is the system we have chosen, passes through the reactor only once. So, whatever conversion happens is because of a single pass through the reactor. So, that is why it is called as a single pass conversion. If we have clear understanding of these terminologies, we can go ahead and perform material balance calculations for systems with recycle and reactions. Let us look at a few example problems which will help us fully understand such problems. Here is the problem statement. Bioreactors are used to produce a wide variety of products such as ethanol, antibiotics and proteins for dietary supplements and medical diagnosis. The figure shows a recycled bioreactor in which the overall conversion of a proprietary component in the fresh feed to product is 100%. The conversion of the proprietary component to product per pass in the reactor is 40%. So, the problem statement tells us that there is a proprietary component which is entering into the system, which is the reactor, and it is getting converted to form some product. We have been told that the overall conversion, which is for the overall system, would be 100%, and we have also been given that a single pass conversion is 40%. You have been asked to determine the amount of recycle and the mass percent of component in the recycle stream if the product stream contains 90% product and the feed to the reactor contains 3 weight percent of the component. Assume that the component and the product have essentially the same molecular weight and the waste contains only water and dead cells. So, here is the flow sheet for this process. So, let us try to convert whatever information we have into this flow sheet. We have been given that the overall conversion for the system is 100% conversion. So, this system which we have chosen, which includes all the components as the overall system, has a conversion of 100% of the proprietary component. We have also been told that there is 40% conversion for the proprietary component which passes through the reactor a single time. So, which means this particular system which we choose, where the component actually passes through the reactor only once, is called as the single pass conversion, and here the conversion is 40% only. So, we have these two information. In addition, we have been told that the product stream contains 90% product and you have 10% component which is entering into the system. So, we also have 3% component in the feed which is entering the bioreactor, which is the gross feed. All this information has been represented in this flow sheet. Now, let us try to perform the required material balance calculations to calculate the required answers. As with any material balance problem, we first need to identify a basis for this problem. The problem statement does not give any mass or flow rates, so hence we can assume a basis. I have assumed a basis of 100 kilograms of fresh feed. So, we have also been told that the molecular weight of the proprietary component and the product can be considered to be equal. This means the reaction would basically be proprietary component C gets converted to product P. So, this can be a stoichiometry which we can assume, indicating that 1 mole of proprietary component produces 1 mole of product. This assumption is valid because we know the molecular weights of these two components are the same. So, now let us consider the overall system and start writing the balance equations. for the overall system, the total balance equation would be input equals output, because we are assuming steady state, which means accumulation goes to 0. So, you have F equals P plus W. We have assumed F to be 100 kilograms. So, this implies P plus W equals 100 kilograms. We can also write a component balance for the overall system. If we start with input minus output plus generation minus consumption equals accumulation, accumulation goes to 0 because there is no the system is at steady state, and for this system we have chosen there is no component which is leaving the system, everything is getting converted to the product. Obviously component is not getting generated because it is the reactant. So, you are left with input equals consumption. So, we know that the input is 0.1 F. We now need to know what the consumption is. So, what would be the consumption? We have assumed that the stoichiometry is 1 mole of component produces 1 mole of product. So, the amount of product which has been formed is 0.9 times the product stream. Based on the stoichiometry that we have assumed, we know that 1 mole of proprietary component gets converted to 1 mole of product. So, we know that product formed is equal to 0.9 times P. So, this should also be equal to the component consumed. So, therefore, consumption term would be equal to 0.9 P. Substituting the value for consumption in the component balance equation, we would get 0.1 F equals 0.9 P. As F is 100 kilograms based on the basis, we can calculate P as 11.1 kilograms. Substituting this value for P in the total balance, we would get W to be 88.9 kilograms. So, we have calculated the product stream as 11.1 kilograms and waste stream as 88.9 kilograms for a fresh feed of 100 kilograms. Now that we have calculated this, we now need to identify what information is required from the problem. The other thing which we need to calculate is information about the recycle stream. As we need to calculate the flow rate for the recycle stream and the composition of the recycle stream, it is important for us to identify an appropriate system. So, this system would have to allow recycle to cross the system boundary. So, for that we could either choose the mixer or this system which includes the bioreactor and the product recovery. We would not want to choose any other system because information about some of the streams which are engulfed inside this system would not be available for us readily. If we were to choose the bioreactor plus the product recovery unit as the system, our component balance can be written as, you have component coming in from the gross feed which would be 0.03 times F prime. This would be, so the component balance for this system chosen, which is the reactor plus the product recovery, would be input minus output plus generation minus consumption equals accumulation. Accumulation goes to 0 because it is steady state. So, you are talking about a reactant, which means the generation term also goes to 0. You would have input, output and consumption terms. The input term would be 0.03 times F prime, which is the proprietary component entering through the gross feed. We know that it is 3% of the gross feed. So, using that we can identify the input. This equals output, which would be the component present in the recycle stream. Let us call that R times X, where R is the mass of the recycle stream and X is the mass fraction of component in the recycle stream, plus consumption, which would be the single pass consumption of, which can be calculated based on, plus consumption which can be calculated using the single pass conversion given to us. So, the single pass conversion has been given as 0.4 this times the feed which is entering the reactor, which would be 0.03 F prime. So, this is the balance equation for the component for the system chosen. If we write the balance equation for the component for the mixing point, so the mixing point as the system, the component balance would be again input equals output, because there is no generation or consumption terms here for a non-reactive process, and accumulation goes to 0 as its steady state. So, this equation can be simplified as input is 0.1 times F plus Rx, which are the input for the components coming through the fresh feed and through the recycle stream, equals output, which is 0.03 F prime. Now, if we were to substitute the value for 0.03 F prime as 0.1 times F plus Rx into the first equation we have, we would get the equation as 0.1 F plus Rx equals Rx plus 0.4 times 0.1 F plus Rx. As we already know the value for F to be 100 kilograms, we can calculate Rx from this equation as 15 kilograms. Now, substituting the value for Rx here, we would be able to calculate what F prime is. So, this equation becomes 0.1 times 100 plus Rx, which is 15, equals 0.03 times F prime, giving us the value of F prime as 833 kilograms. Now that we have the information about fresh feed from the basis as 100 kilograms and the gross feed from the calculations as 833 kilograms, we can write the total mass balance for the mixing point to find the information about the recycle stream. The total mass balance for the mixing point would be F plus R equals F prime. This implies R equals 833 minus 100, giving a value of 733 kilograms. Now that we know that the recycle stream is 733 kilograms, we can calculate the composition of the component in the recycle stream from the value of Rx. We know Rx is 15 kilograms. So, X equals 15 divided by 733, which is 0.0205. So, this is the mass fraction of the proprietary component in the recycle stream. With this, we have calculated all the required values in the problem. Let us move on to another example problem which uses similar concepts and which will give us further clarity on performing material balance calculations for systems with recycle. Here is the second example. Immobilized glucose isomerase is used as a catalyst in producing fructose from glucose in a fixed bed reactor. For the system shown, what % conversion of glucose results on one pass through the reactor when the ratio of the exit stream to the recycle stream in mass units is equal to 8.33. So, you have been given information about the fresh feed, the gross feed, and you have also been given the information about the ratio of exit stream to the recycle stream. With that, we need to calculate the percentage conversion for a single pass through the reactor. Let us see how we go about this problem. As with any material balance problem, the first step is to identify the basis for the problem. Here, no masses or mass flow rates have been given, so we can assume a basis which is convenient for our use. So, here I have assumed 100 kilograms of fresh feed as the basis. So, basis is 100 kilograms of fresh feed. If we were to consider the overall system, the total balance for this system would be P equals F. As we know, F is 100 kilograms, P would also be equal to 100 kilograms. The problem statement tells us that P divided by R equals 8.33. This implies R is equal to 12 kilograms. So, we now have information about the product stream and the recycle stream. In addition to writing the total balance equation, we can also write component balance equations. For writing component balance equations for the overall system, we need to understand what reaction is taking place. We have been told that glucose is being converted to fructose using an immobilized glucose isomerase. Glucose is C6H12O6 and fructose is also C6H12O6. It is just an isomerization reaction which is happening. So, only glucose is involved in the reaction and fructose is being produced in the reaction. So, hence we know water is not taking part in the reaction. If we were to write a component balance for water, it would come down to input equals output. So, let us do that. Water balance equation would be input equals output. So, input water is basically 0.6 times F. We need to calculate output water. So, let us call the mass fraction of water in the product stream as XWP times P. So, let us label what these are. So, P would be the product, XFP, XGP and XWP are the mass fractions of fructose, glucose and water in the product stream. Similarly, we would have R as the recycle stream with XFR, XGR and XWR as the mass fractions of fructose, glucose and water in the recycle stream. However, one important information we have from the flow sheet is we do not have any separator, we only have a splitting point. This means the mass fraction of fructose, glucose and water in the recycle stream would also be the same as the mass fractions seen in the product stream. So, this means these values would also be XPF, XPG and XPW. We can assume the total feed entering is T with XWT and XGT as the mass fractions of water and glucose in the gross feed entering. So, this information can be used. Now, coming back to the balance equation we had, we can substitute the values for F and P into the water balance equation for the overall system to calculate XWP as 0.6 again. So, now the next step is for us to get information about the mass fractions of the product streams, recycle streams and the gross feed. So, for finding this information we need to choose an appropriate system. If we were to choose the splitter, we would be able to write only one independent balance equation. Hence, it would not help us in identifying all the unknowns. So, we can choose the mixing point instead, where we would be able to get more independent equations and hopefully we will be able to solve for the unknowns. So, let us take the mixing point as the system. So, for that we can write a total mass balance which would be T equals F plus R. So, you have input equals output. So, you have T equals F plus R. So, which means T equals 112 kilograms. We can also write balances for fructose and glucose. The fructose balance for the mixing point would again be input equals output, and input fructose is 12 times XFP and output fructose is 0.04 times 112. So, this means XFP is equal to 0.373. Now that we have the mass fraction of fructose and water in the recycle stream, we can calculate the mass fraction of glucose in the recycle stream also. So, that would be XGP would be equal to 1 minus XWP minus XFP. So, this equals 1 minus 0.6 minus 0.373, giving the glucose mass fraction as 0.027. Now that we have the mass fraction of glucose in the recycle stream, we also know the mass fraction of glucose in the fresh feed, we can write a glucose balance for the mixing point. So, the glucose balance for the mixing point would be input equals output, and input is basically 0.4 times F plus 0.027 times R equals XGT times T. We know the values for F, R and T. Substituting those values, we can calculate the mass fraction of glucose in the gross feed as 0.36. As we have the mass fractions of glucose and fructose in the total feed, We can also calculate the mass fraction of water in the total feed. So, which would be XWT equals 1 minus XGT minus XFT, which equals 1 minus 0.36 minus 0.04, giving a value of 0.6. We still need to calculate the single pass conversion for the system. For calculating the single pass conversion for the system, we need to identify an appropriate system to study. So, the appropriate system would have to allow the reactants to pass through the reactor only once. This means we need to ensure that the total feed is what is crossing the system boundary. So, we will choose the fixed bed reactor with the splitter as the system for our study. So, this would ensure that we have information about both the product stream and the recycle stream, which are the exit streams, and we also already know the information about the inlet stream, which is the gross feed. With all this information, we will be able to calculate the fraction conversion for glucose entering into the fixed bed reactor for a single time. So, now let us write the glucose balance for the system chosen. The glucose balance would be input minus output plus generation minus consumption equals accumulation. At steady state, accumulation goes to 0. Glucose is not generated as it is a reactant. So, the equation simplifies to input minus output equals consumption. So, we are expected to calculate consumption. So, the consumption is nothing but input minus output. Input is TXGT and output is R plus P times XGP. So, substituting the values for T, XGT, R, P and XGP, we can calculate the consumption as 37.296 kilograms. Now that we have the consumption, we need to know how much glucose is entering the reactor. Glucose entering the reactor, which is input, would be equal to TXGT. This is equal to 40.32 kilograms. So, single pass conversion would be glucose consumed by a single pass, which is 37.296 divided by glucose entering, which is 40.32, giving a fraction conversion of 0.925. So, this is the single pass conversion for the system given. With this, we have performed some example problems to get a full understanding of what recycle systems with reactions would be. See you in the next lecture. Until then, thank you and goodbye.